In this video, we're going to take a look at a couple of subsets of vectors in R3. So our vector space is R3. We're going to determine if the following sets are bases. So first thing we should point out is that the dimension of R3 is going to be equal to 3. In general, we refer to Rn as n-dimensional Euclidean space, and that's why R3 would be considered three-dimensional space. So with that in mind, taking a look at part A, we have a set containing 4 vectors, which is 2, 1, 3, 3, 2, 1, negative 1, 0, 1, and negative 2, negative 2, negative 2. So first thing to point out is that because the dimension is 3 and the number of vectors does not match the dimension, it is impossible for this thing to be a basis. And here's why. So because the dimension of our vector space in question is 3, and the set contains 4 vectors, the set is guaranteed to be linearly dependent. And because it's linearly dependent, we can draw the conclusion that it is not a basis. A basis is defined as something that is both linearly independent as well as a spanning set. So because this one is linearly dependent, it means that one of these vectors is guaranteed to be expressible as a linear combination of the others. As such, it is not a basis. For the set in part B, we do have the right number of vectors this time, since the dimension of our vector space is 3, and we have a set containing 3 vectors. However, I would like to point out that if we were to label these 3 vectors as v1, v2, and v3, we can make a note that states that if I were to multiply v1 by 2, I would get exactly the vector v2. And if I were to take 3 times vector v1, I would get exactly the vector v3. As such, because we can express these vectors as linear combinations as linear combinations of one another, we can conclude that the set is linearly dependent. So same issue as with part A. Therefore, this will not be a basis. Now for our third example, down here at the bottom of the page, we have a set containing 2 vectors. Those 2 vectors are 2, 0, negative 3, and 3, 8, 5. Now, because the dimension of our vector space is equal to 3, and the set contains only 2 vectors, the set will not span our vector space. So because it won't span, we can conclude that this set is not a basis. So too many vectors, guaranteed linearly dependent. Too few vectors, guaranteed will not span. And in either case, it is not a basis. Now flipping over to the other side of the page, we also have this set of vectors in R3. 4, 5, 2, negative 1, 0, 5, and negative 2, 1, 6. So with that in mind, we do have the magic number, and I don't believe that any of these is a scalar multiple of the other. So as a result, what I'm going to do is set up a linear combination of these, and we're going to see if this is a linearly independent set. So we'll do C1v1 plus C2v2 plus C3v3 is equal to the 0 vector, and that'll test for linear independence. So what we'll be setting up is C1 times the vector 4, 5, 2 plus C2 times the vector negative 0, 1, 5 plus C3 times the vector negative 2, 1, 6. We'll be setting that equal to the 0 vector 0, 0, 0. So what we'll be setting up is an augmented matrix. It'll be a 3 by 4 augmented matrix representing the first coordinate, the second coordinate, and the third coordinate of each of these vectors, or components I should probably say, and comparing the coefficients of C1, C2, and C3. So for the first vector, C1, first component is 4, then 5, then 2. For the second, we'll see negative 1, 0, and 5, and for the third we'll see -2, 1, and 6. The augment is 0, 0, 0. I intend to take this down to reduced row echelon form, and I have absolutely no intention of doing that by hand. So let's turn to our handy-dandy calculator that we always seem to have close by. Entering the matrix menu, I'm going to go to Edit. This will be a 3x4 matrix. First row will be 4, -1, -2, 0. Second row, 5, 0, 1, 0. Then we'll see 2, 5, 6, 0. And I'm just going to check, make sure that everything got copied in here correctly. First row is 4, -1, -2, 0. Then 5, 0, 1, 0. 2, 5, 6, 0. Very good. Then we'll ask the calculator from the math menu to take this down to reduced row echelon form. Reduced row echelon form for the matrix A. And we see that we wind up with the identity matrix to the left of the augment, and the augment itself is simply a bunch of zeros. Identity matrix augmented with a bunch of zeros. This implies that C1, C2, and C3 are all equal to 0. Because only the trivial solution exists for this, we can conclude, therefore, the set is linearly independent, and there is a theorem that states when you have the same number of vectors as the dimension of the space, then if the set is linearly independent, it is automatically a spanning set. Therefore, the set is a basis. Hooray!